Okay, sorry, I go too fast.
That's fine.
Sorry.
That's fine. You're too fast.
Yeah.
Okay, so so now we have the pleasure of welcoming Tat-Dat, who is an associate professor at Université, Sorbonne Université in Paris, and he will talk about machine learning and wavelet theory applied to the epidemic dynamics. Okay, please start.
Okay.
Whenever you're ready.
Okay. Thank you very much for inviting me for the seminar. It's the first time for me to talk at the application seminar like this. So using applied mathematics. So for me, it could be a very big pleasure. So further, I would like to talk about the title. The title at the beginning should be Epidemic Dynamics via wavelet theory and machine learning and application for COVID-19. But because it's very long, so I remove the COVID-19 here. So of course, the main data will be used in our numerical results should be in using COVID data. Okay. So further on, we just look at some very simple model for epidemics, so-called SIR model, which is a compartment model defined by three number: IT, ST, RT. So it's very classical one. And for the dynamical equation, we can see that for the number of infectious in video, you can see that the graph of the number infected individuals looks like the curves in the graph I draw here. So when the parameters, when the initial condition changes, in fact, the form of the graph should be go up very fast and then go down less fast than go up. So that's the graph of the number infectious individuals with respect to SIR model. Why I show here this kind of model? Because when we see that in the graph, in fact, there is only one wave appears. I mean, wave is that mean one the one go up and go down here. Then similarly for other modifications of SIR model, the curve of infected individuals always go up and go down, but only one wave. So that's situation is very classical and somehow appears for some disease which will be well controlled for a short time. I mean, maybe several months or 1 year after having something like good measures or vaccination. But in contrast of this situation, for the COVID-19, we don't have this situation because we have several ways which comes after short times like 2 months or 3 months. So for example, in France, we are the first ways we are from, I mean, maybe from March, and then go up and go down with confinement restriction measures. Then after that, we remove the measures, the second wave coming, and now without the strict measure, the number of infected individuals always go up like this, and then you can see that recently it's go down a little bit. So the same ways for the same thing for the USA, we have several waves appear, something like this. So that turns out that the classical models like SIR or its variations will not be compatible with this situation of COVID-19 if we consider only one dynamical model like this. So the idea from this situation of COVID-19 is that we must find something like a multiple ways model. I mean, a model which have several ways possible. So the total number of new cases will be the sum of several different ways. I mean, different curves. Each one maybe presents for sub-epidemics. So the name of sub-epidemic maybe appears a long time ago, but the thing is that we must to combine sub-epidemics because sub-epidemics maybe appears in times, in different times or different locations. So in general, the daily cases will be combinations from different location or different sub-epidemic depending on time as well. So this idea is, in fact, you can see that if consider the daily case as a functions, that means we must decompose this function as a sum of several functions. So this exactly is the idea of decomposition of function by wavelets in mathematics. So what is the wavelet? Which is in fact a wave-like oscillation with the amplitude that begins at 0, increasing, then decreasing, and back to 0. So in the wavelet theory, we study the decomposition of functions, maybe from the open interval to R, and try to decompose this function like the sums of some wavelets functions. So that's the idea. So if you consider F is like the number of daily new cases of COVID-19. So each W1 up to Wn maybe presents for the number of daily cases of sub-epidemics. I mean, of sub-epidemics which present for a location or for a sub-epidemic in time. I mean, the total number should be combined by many other numbers. Okay. So that's why we try to from this we try to define some some objects or something like some functions, so-called epidemic-fitted wavelet. The idea is that we try to find some function which define on some interval AB, and his value is positive, which describes for the effective daily cases, which on homogeneous population with respect to an epidemic or maybe say sub-epidemics that occurs in only one way. I mean, this W here should be one a small w in the decomposition of the function f here, if f is a daily case number functions. Okay, so which is wavelet in mathematical point of view. So a wavelet or Maser wavelet is a function psi, which is integral. So here I take R, but you can reach it on some interval AB. So such that we have this condition is C size is not finite. So where in this integral psi hat is a Fourier transformation of psi. Okay, so the class of this kind of function, you can see that, for example, the wavelet function very well known is psi t equal to sine 2 pi t minus psi pi t over pi t. So that's kind of wavelet function. From one Maser wavelet function or from some wavelet function, we can generate other wavelets by adding some parameters. For example, here you have a function psi here, and you can add AB as parameters. So AB here is parameters. Sorry for I use the same characters for interval and for parameter. But let's say AB is parameters, and then psi ABT is divided by psi by rotation, I mean scaling time variable and adding some constant. Okay. So a theory of, I mean a theorem in the Wavelet theory is the decomposition in N2 space. If you have psi be a master wavelet, then for any function f in N2R, this function can decompose like f equals this. So this means if you take the limit from f minus the standard product in L2 from f and psi AB. So the psi AB is a function obtained from psi adding some parameters A and B. So this the equation 2 means the limit from f minus psi c psi minus 1 of the integral from the N2 product of f and psi AB in the N2 norm tend to 0 when the intervals here tend to infinity. I mean the parameter A will come from 0 to infinity, and also for the parameter B. So in this writing version, you can see that f will be the sum. F will be approximated by the sum of the projection from f into the space of function psi AB times psi AB. Okay, so that kind of decomposition of function by describing sum, replace the integral by the sum. So we have the describing the versions of this theorem. I will not present here this result, but it's well-known result for the decomposition of L2 functions in wavelets. Okay, so from this idea of wavelet theories, we try to define something similar. The first one is that we try to define which is called epidemic-fitted wavelet, which is a real function on N1 of some interval AB, such that psi has the shape of start peak stop. That means psi is increasing near A, decreasing near B, and psi at is maximum at some point in AB. Okay, so it's, you can see the graph of psi like the graph of the Gaussian function. It's from A is increased to the maximum, and after that is the function decreasing. Okay. So for example, here I put two examples, simple ones. The first one is exponential. So e to power x squared over 2. The second one is log normal function. So here log normal, I mean sorry. Okay, so log normal, I mean that changing x in the Gaussian function by log x. Okay, so from this we can have a new function which has the shape like start peak stop, I mean increasing, then attain maximum, and then have and then decreasing. Okay, sorry, maybe it's a problem with myself. Okay, so other examples for the epidemic-fitted wavelet is some distribution function like Gomper's functions, or you can take the function IT, the infectious individuals number. IT is the SIR model. I mean, IT is implicit functions, which is solution of SIR systems. But suppose that you have this solution, you can see that this function has the behavior start peak slope, I mean increasing, then attains its maximum, and then decreasing. So we have a lot of functions which satisfy the definition of epidemic-fitted wavelet we need. So now come back to the our purpose is that we would like to see which is the behavior or the dynamics of the number of daily reported. So this number is one of the important number. So if we know for next, for example, next weeks or next 2 weeks, which is the behavior of the curve of daily reported case, we may have some measures to control this number. So that means if we can have some forecasting on the number of daily case, we can have some measures to control this. So that's why we first interested in the daily reported cases. I mean reported. Of course, you know the number from some reports from hospitals or some other resources. And then the model for the number of daily reported case, you can present as a finite linear combination of epidemic-fitted wavelets. I just devised the last slides. So RC, so R for reported, C for case, reported case at the time T should be can be explained or can be represented by the linear combination of Wi T theta T. So here such wavelet Wi can be obtained from the Marzer affected wavelet side by adding some parameter. So as in the mathematical wavelet, given a wavelet Marzer wavelet side, you can generate many wavelets using some parameter by adding some parameters. So here's the same. Given epidemic-fitted wavelet size, you can generate other wavelets Wi here by adding some parameters theta I. Okay, so this kind of the decomposition of the functions as the linear combination of wavelets I just present previously. And okay, so if you come back with this equation, we must to find the parameter theta such that the curve of reported case is close to this sum, right? So this problem finding parameter theta I is exactly a problem in machine learning, so-called curve fitting problem. So you have a curve of the curve of reported case. So you must to fitting this some functions in order to find theta I such that this curve, the original curve, will close to the sum of other curves. Okay, the linear combination of other curves. Here the parameter, sorry, here I just missed the parameter B. Here we have two kind of parameter. The first parameter is for the wavelet here. Okay, so the parameter theta should be like something like slope of slope or the velocity of the curve present for this kind of curve. Alpha I should be the parameters present for the amplitude of the curve of the functions. So we have two kind of parameters: parameter theta I and parameter alpha I. Okay, so finding alpha I and theta I should be a curve fitting problem in machine learning. Given the data is the curve reported cases, we must to find these parameters. Okay. So one example I will present to you, in fact, is a very simple model. So I consider the log normal functions as I present you previously. You have the exponential functions, Gaussian function, and we change x by log of x and adding some constant b and c. Then you can even have a new function called log normal functions. And then you can see that the graph of the log normal functions is quite similar to the curve of infectious individuals in SIR model. So it should be 0 at the beginning and go up very fast, and then go down slower. That's kind of the form for the log normal function. It's contrast with the Gaussian function, because the Gaussian function is quite symmetric functions. So it's go up and go down, it's the same shape, same velocity. So it's somehow does not present the curve of daily nucleus in epidemics, because in epidemics at the beginning the daily nucleus will go up very fast with exponential velocity, and then go down slower. Okay, and then that's why I choose the log normal function instead of Gaussian function. Okay, and now our model for log normal function is containing the combination of sorry, here I train again one time the name of parameter. Here we have the sum of n wavelets psi BICI. So again BICI here psi BC say here is a function of exponential log x minus b square over 2c square. Okay, so here BC is parameters. So here I take the sum with the coefficient AI, and with the log normal function psi BICI. So I would like to find the parameter AI BICI such that the curve WT is close to the curve of daily reported cases given by some resources I mean online resources like Johns Hopkins database or window methods database. Okay, so here I just repeat with IBC so that W is close to the daily infected number as CT. So this number is given by available resources from some resources online. I mean, which is given by for me. I take the data from dataset from Johns Hopkins University, and we can take ICT is daily reported number from window methods. I mean, the number is quite similarly, it's quite the same, but of course there is some difference, but it's not, it makes no problem here. So I mean, you have a model is WT, you have data is RCT. So now the main thing is that you find parameters such that WT is close to RCT. Okay, so once you get the parameter, you have the model, and then from this model you can say something like forecasting for next 2 weeks or next months, something like this, of the daily look case. Okay, so to compare WT and RCT, we must have some loss function. Loss function, I mean the function which measures the difference from two numbers. So here, for my experiments, I will use the Euclidean distance function for the loss function. I mean, you take Wt minus Rt square, and then I minimize this quantity when t run from the first day to some days. T is the variable run from an interval of times. So numerical result here, I will present some result I run a long time ago. I just because I just I run this because we put it in our paper, which paper already accepted and available. But here I would like to use these images again. One reason is that I don't have time to run on experiment again. Yesterday, I just opened my laptop, but after that I cannot run in time to present to you all of the prediction. But at least I can show you the prediction we made a long time ago. Is from 20 in the October last year, 25. So for example, here I use 5 ways. I mean 5 wavelets function to combine 5 wavelets function to approximate the reported daily case of Czechia, so Czech republics. And you can see that here, maybe it's okay for you. Can I zoom out like this? Okay, so here you have a curve, the green curve here. The green curve is the curve Wt I just present in the last slide, which is the sum of other curve. So here you have a sum, the red curve here, the pink curve, the blue curve. So each curve here, small curve here, thin curve, is a wavelet, a graph of a wavelet. And then the green big curve here is the sum of 5 curve, 5 thin curves. So here you see that there are only 3 curves appear, but in fact other curves is almost 0. You can see in this X is there are some colors like I say 0, 1, who say almost 0, because the coefficient AI is quite clear 0, so it should be 0. And as a wave, you can see that appears for this and this term. So you can see that the curve, green curve here, is quite close to the data. And then from this, I use the data from the beginning of the epidemic until the 24th of October, until this vertical line. And then from this vertical line to later, I mean this is forecasting for the daily new case of here is for 2 months, I mean. Okay. So here, for example, I keep for the validation, I mean, see if our algorithm is work well or not. I keep the data from the beginning of epidemic until the 18th of October, and then use I mean 6 or 1 week later for validation. I mean for compare this black dot here is the real data, and this black dot here is not in the training data. I mean in the data for fitting the curve. So it means that we do not use this data, but this data with respect to our forecasting is quite close, right? And then you can then for France, for example, we do the same thing for the prediction, but of course here for the validation we have a week, and then so it's go up. So that means we have new epidemics appear, but we have something not very close from the prediction and the real data. And after that, we have Germany, for example. So Germany, we have several ways. So here at the beginning, you have, you have the first wave here and combined with the second wave, and then it's go down, and then it's go up with two new epidemic, sub-epidemics. So the first one is the red one here, new sub-epidemic, and the second one is blue one. Okay, so it's each curve here, the blue and the red and other colors is correspond to the log normal wavelet I just present last time, and each one I just present in last slide, and each one correspond to a sub-epidemic. And then we have the green one, green big one is combining, the sum of these wavelet. So the same, we try to use the data from the beginning until the 18th November and keep 1 week for the validation. And you see that the prediction of our curve with the validation set is quite close as well. Okay. The same thing for Italy. So I just go here. So you can see that Italy, we have several curves here correspond to wavelet functions in the sum of WT. And then the WT is exactly the green curve, which is the sum of each small curve here. And then here you can see that it's very fit with the prediction and the validation, the real data set for 1 week. Okay. And of course, we need to, sorry, I must view full screen. We try to compare our approaches, our approach with other one. For example, something like very classical is a simple moving average method, and ACMA, so it's called auto-regressive moving average, or ARIMA, something like this. So for this kind of stochastic methods, we choose some parameter for them, and then we try to see what happened when we use these methods with compared with our methods. So we see that for example, for Czech Republic, for the beginning of the epidemic, so if you see is a color here, the green one, big one here is our model, log normal model. Other curves is come from ACMA here, SMA, the simple moving average for the blue big one. The green one is ARIMA. Okay, so you can see that the behavior of simple moving average is quite straight. For the ARIMA model is quite go up and go up. The ACMA is quite good. At least ACMA is quite good, but our model have the good step, the best step here. And the same for others. For here, I just try to use data from the beginning of the epidemic for Czech Republic, Germany. You can see that something the same. Our models will go up and then go down, but other they have the tendency like go up. For simple moving, it should be go straight line. And it's the same for Italy. So we can see that the green one, our model, go up and then go down, and other one is quite good as well, but it go down very fast. Okay, so here for the second situation, I mean, after the peak, it should be go down like this, and then you can see that other method also say that it should be go down. So, but our model is quite close to the real data. I mean, yeah. So here you can see that we are a sub-epidemic up here, and okay, and then the combination of two epidemic, sub-epidemic give the reported case, daily case of on Italy here. Okay, so I just take quite a lot of time, but it's quite almost thing to do. So so the next direction, how to go? Okay, the further direction for this study maybe we can try to use the wavelets models for other numbers like active cases, daily deaths, to understand which will be happen in the future, and then we have some measure to control. The second thing is that we can use other wavelet function. Here we just used the log normal function, but of course you can use other functions. So suppose that you can use effective individual function IT in the SIR model. So in SIR model, you have some parameter alpha, beta, gamma. So to fit with the reported case, that means you must find the parameter alpha, beta, gamma, such that we have the good approximation from the real data and the curve. I mean, IT may be used as a wavelet in our method. So we can extend wavelets as a multivariate functions. I mean, the function depend on many variables. So here I just use the function use one variable on time, but of course we can use other variables like the measurement levels, or other one like death rate, recovery rate, etc. Okay, so here should be nice direction, but of course we must to use many resource, computer resource for dealing with, and of course try to find some good methods for the curve fitting problem. I mean, finding a parameter, we must to solve the optimization problem, and how to choose the good one is one also problem. So as a bonus, I have succeed to run only for Germany. Yesterday, today I just run for Germany. But here you can see that the curve from July to today, here is a green curve. Is close to the real data, and for the forecasting for next few weeks, it should be increasing like this. I don't know if it's correct or not. We can see, but this is our result for the data from July until yesterday. Okay, so it's prediction from today. Okay, thank you for the participants, and if you have any question, you are welcome.
Okay, thank you, Tat, for an interesting talk. Yes. I will open with a question regarding your last slide. So in Germany, it looks like you are missing a phenomenon between, let's say, November 2020 and January 2021. There seems to be a kind of oscillation that is not captured by your model. Do you think that it could be solved by adding wavelet to the system. So instead of 5, using 6 wavelets.
Yeah, you're right. You're right. Because here you can see that this kind of oscillation, we can adding some other wavelet. The number of wavelet could be maybe 6 or 7, or maybe increasing as you say. But the problem is that we can adding this, but we must to sure that the optimizing method can give a good result to, I mean, for the parameter of own 6 or 7 wavelet to appear here. So here you can see that we have 1, 2, 3. 1, 2, 3. So we try to use 5, but here you see that we have only 3 ways appear, and other is 0, something like this.
What are the wavelet you are using here?
It's the log normal one.
The normal, what?
Log normal.
Log normal.
Okay.
And so this leads me to my next question, which is how do you choose the number of wavelets?
Yeah, so that's a very nice question. For the number of wavelet, we have some strategy to have this something. You can maybe you can make the statistic from the data and see that the measures of oscillation of the data, and then see how the variation of the real data to find the number of wavelet. So that should be a math problem, but statistical one. But in fact, for this result, I try to use 5, but because 5 is quite enough for approximate. But in general, if we have a lot of wavelet, we must use statistic to choosing the number of wavelet. For example, you can increasing the number of wavelet like 10, and after that running the optimization, you see that there is 5 parameter alpha AI very close to 0. I mean, we have a 5, 1 which is redundant. So you can remove 5 wavelet and keep only 5, 1 to approximate the curve. That is one way to see which is number we will use for the number of wavelets here.
Okay, so increasing the number of wavelets does not necessarily increase your the quality of the fit of the model.
Yeah, right. You see, if we have a lot of wavelets, when you fit to the optimizing problem, that can give you a lot of solution, not only one solution. If the number of wavelet is compatible with compatible with the oscillation of the real curve, the optimization problem should give a good result. But for example, here when I run with the code with this kind of data, I got 2 results because the initial condition, or because of the algorithm of optimization. I got 2 results. The one result is something like the curve, something like this. Okay, only one curve. And when I train a little bit, I run again, it goes with this result. So that's why in the new further direction, I say that we must to find some good method for optimize for the curve fitting problem. I mean, such that the algorithm optimization algorithm give us the like a global solution.
So you're saying that you can easily be stuck in a kind of local minimum during the curve fitting problem, and you don't know if this one is the best one or if it could be improved.
Of course, from the loss value, the loss function value, you can see that one is the best. For example, you take a loop and you train the initial condition and you run the optimization. Each one give you a result for the parameter and also for the loss value, and you can choose the loss value which is small. So for the best parameter. But of course, for doing that, you take a lot of times.
Mm-hmm.
If the first one you didn't get the good result, they run to the next one by changing initial point, and then go around, go like a loop, something until you got a good parameter. So that's why it takes a long time. So that's the reason why I put in the further direction how to choose a good methods for optimization curve fitting problem.
Yeah. I'm still I don't know this. I have a hard time to imagine that this oscillation in the middle cannot be predicted. It's, conceptually, it's difficult for me, but that's just my problem, I guess.
But in fact, for the oscillation here, if the curve, I mean, if our curve is go up like this and go down, maybe the peak is go up a little bit. So it should be very good already, because you see that the oscillation here maybe depending on many things. Maybe the reported case is not good. I mean, the number of reported cases is missing something, or maybe there is some delay of reported cases. It's go to the oscillation, something like this. But assuming that the curve go up a little bit and go down, I mean, it's quite close to the real situation. I mean, so I don't know, but let's say the trending, the tendency of the curve, it should be something like this, go up and then something go down. But maybe from something like I say that from the strategy of each countries, maybe from this part, Germany gives some measurements, strict measurement on this country, then the numbers go down, and then the curve is not something like this. You see, so so that's why in a further direction I put inside as well that the wavelet should depend on many variables, on not only on time but on the other variables like the measurement level is strict or not. If it is strict measurement, the curve should be go down fast. But without the measurement, the daily new case should go up, and go up, and maybe go up until everyone got infected. I mean,
may I ask a question?
Yes,
in fact,
please. I was going to ask if anyone had a question.
Okay.
Yes, Jean-François, you have a question? Jean-Pierre?
Yes. In fact, do you see these small oscillations only on Germany?
No.
We can see maybe as a, it depends, maybe in I don't know, maybe in France as well, not only in Germany. In France here is quite, sorry, but maybe I can share, I can show you in the Bordeaux.
In fact, there are huge fluctuation in some countries, daily fluctuation. There are problems with in reporting the data, for example, and and so it's pretty difficult to.
Okay, but it's only on these curves, on this data that you show this.
No, I mean in other countries like in France as well, they have some oscillation like this. I can show you. I stop sharing this screen, and then
I have another question. In fact, yes. Okay.
Let's wait a little bit. For example, here in France, you see that?
Yes.
Yes, there is oscillation here. So it's go up, go down, but it's go up, then go down, and then go up, and then go down. It's quite.
It's similar. Okay.
Yeah, it's not only Germany, but for example, in USA is same thing. You see that? Okay. Go up, go down, go up, go up, go down, go up, go down. It's depends many things, but of course the delay of reporting, the measurement of the government, and many things is need to this situation. And that's why in my talk I would like to say that we need to define some wavelet many variables. For example, measurement level. Okay.
And we stay with the United States right now. One of the concerns, or the main concern in the United States right now, is that we are entering a new wavelet. So if you move your pointer just to the very right end, the question is that the head of the main health agency, the CDC, expressed concern that we are about to enter a new phase based on simply the idea that the curve is no longer going down, but looks like it may be going up. How can we resolve this problem? Because if we assume that we have no wave, your forecast will say it will continue to go down. If we assume that there is a new wave, then you have so little data to predict the velocity and the height.
I see the question, but of course, in our method, maybe we can predict a new wave before it's coming. Not before it's coming, but detect the new wave just when it's just coming. For example, I stopped to sharing here and sharing again my my slide, and I can show you what is the situation. Oh, sorry, my son, he crying. So here, for example, maybe I can show you another prediction, another thing from here. You can see that, for example, here the curve, from this, they have some tendency to increasing, right? And then we have already a sub-epidemic here, the blue one. But from this term, you see that there is something go up. So there is a new wave appear in our model. But it's quite not clear, but maybe I see another one. No, it's not here. But I mean that, for example, here, you see that the new wave already coming, but that's coming maybe half months. So our model just predict that the new wave here coming here. You see this blue one, and then so that's it. I mean that if the data have some tendency like it will be increased or new waves coming, maybe in our model we can see a new wavelet coming. I'm not sure, for example, the data of USA, as I show you, they have some oscillation at the end of data last few days. I don't know if our methods can say something for the next 2 weeks with new ways or not. I don't know. We must to run the algorithm. This not in fact is not the thing to prove, but we should run by numerical experiment. I don't know, but maybe I try to say something here. Okay.
So maybe.
Okay, maybe it's time to close the seminar because it's already been 1 hour. So thank you
sorry,
again. Thank you again, Tat, for a very nice talk, and we'll see each other. Well, I hope in 2 weeks for the next session, right?
Okay.
Okay.
Thank you.
Okay. Thank you.
So
Bye-bye.
thank you.
Bye.
Bye bye.